Many times in statistics, you're going to be wondering how two variables interact with each other, how they affect each other, maybe. In this chapter, we'll be talking about scatter diagrams and linear correlation, lines of best fit. And we've seen these before in algebra classes where you have some data plotted on a graph. Because we have the two axes, we have two data sets, and so we can think of those as two variables that correlate with each other. We're going to talk about the x variable as the explanatory variable, and the y variable is called the response variable. In general, we'll try to think about the x explaining what happens with the y variable. So if we were going to apply some sort of treatment in an experiment and then we were going to do a survey of the results, we would hope that the treatment explains the survey results. We would hope, for example, the number of therapy sessions would explain why anxiety was going up or down. And in this case, the way that I drew this scatter diagram, as the number of therapy sessions increased, we saw that the anxiety was coming down, which would be desirable. So this first section is just focusing on that correlation between those two variables. How well the data correlates can definitely be seen on the graph, but we want to talk about that in sort of a more specific way. We are going to talk about correlation. And that first example I showed you was an example of negative correlation because as the x values increased, the y values decreased. But of course, in some cases, as your x value increases, the y value will be increasing. And I think the easy way to see that is that all of these have a positive slope and all of these have a negative slope. And so that would tell you the difference between positive correlation and negative correlation by the looks of the scatter plot. You'll also notice that for some of these, a straight line is a better fit than for some of these other ones. And so when we talk about how well the line fits, that's talking about the type of correlation. So that was a perfect positive correlation if a line goes right through all of those data points. If it's pretty close, we would call it a strong positive correlation. And if there were, maybe some that are further away from the line, that would be a weaker positive correlation, but still positive because that line is slanting upwards. Same for our negative correlations, perfect, strong, and weak, just depending on how close those dots are to the lines. If there doesn't seem to be a line that would really fit the data at all, you can't really tell if it'd be sloping up, down, or left, right, we would say that there's no linear correlation to that data. Now we're going to get way more precise with that in this section. We're going to talk about a number that describes how much of a correlation there is, and that's called the sample correlation coefficient, R. We'll use the letter R to stand for correlation coefficient, and that value will range from -1 to 1, depending on how strong the correlation is. And so a perfect positive correlation will have an R of 1. A perfect negative correlation will have an R of -1. If there's no correlation, you'll see a value close to 0. And then maybe a strong positive would be maybe a 0.97. I'm just making that up. And a strong negative might be a -0.97. Weak, I don't know, maybe an R value of 0.6, or definitely an R value of -0.2 would be very weak. Now I definitely just made up those values, so don't you wonder, is there a way to actually calculate the correlation coefficient? You bet there is. Here's a lovely little example. I've got these already set up with an X matching with a Y, and those are all plotted as points on the scatter plot. I ran my one variable statistics on those, so I have my mean X value and my mean Y value and my standard deviation for both groups of variables. And the really interesting thing is that if you plot the mean X, comma, the mean Y, it actually shows up as a point that's pretty well aligned with that data. Do you see that? And so you'll see in the defining formula, we're going to be looking at how far each x and y value vary from their mean. And actually, we'll look at the product of those. The standard deviations get involved in the number of points, and that will help us find the correlation coefficient. Let's try it. So since there's 4 ordered pairs, I know that my n equals 4. I need to figure out what the sum of those x minus x bar times y minus y bar values will be. That'll probably be the most complicated part of this. So let's do x minus x bar for each of those x values. So I've got 1 minus x bar, 2 minus x bar, 3, and then 4. And let's do the same thing for the y values. Y minus y bar. Since we're multiplying those together, we're going to take our x minus x bars times our y minus y bars. The sum of all of that is 15, and so we're done with that calculation. And that was the major part of the defining formula. So let's see if we can use the formula now. So r, the correlation coefficient, is 1 over n minus 1 times that sum that we just found over the sample standard deviations multiplied. So here's Sx and here's Sy. Comes out to 15 over 14.9769, which is 1.001. And technically our correlation coefficient should never be above 1. I'm thinking that that was just a correlation coefficient of 1, which tells me I made a mistake, because I was expecting that to be a negative r value. So what did I mess up? It was when I summed all of those together. That should have been a negative 15. Good thing I'm smart. I figured out my mistake. So my correlation coefficient wound up being -1 once I round it, which means we should have a line that fits through there pretty perfectly, right? That formula was kind of cumbersome, and this one looks even worse, but it's supposed to be a little bit easier. Again, n is 4, since we have 4 x's and 4 y's. We can use that one variable stats to figure out what our sigma x and sigma x squared are, remember? So that was 10 and 30. $42 and $4.86. And this last calculation will be a little more annoying because we have to take each x times its y and then add those together. So 1 times 15, 2 times 12, 3 times 9, 4 times 6, which comes out to 90. Anyone want to see how the calculator can get that piece? If we go to stat, calculate, you'll notice that there's a 2 variable statistics. And if we have list 1 and list 2 in there, if you go down far enough, you see where that 90 shows up? The sum of x times y equals 90. So that's a nice place to get that calculation too. But I certainly want you to know how to figure these out by hand as well. That was pretty quick with the help of our calculator. Let's see how the formula goes. R equals n times sigma xy minus sigma x times sigma y. That's not too bad. Like I said, it looks scarier than it is. On the bottom, a couple square roots. This one is n times sigma x squared minus sigma x squared. You'll see the difference between those. Same thing, only y values. Pretty sure if I tried to type all that in with parentheses, I'd mess it up. So I like to type in just the top and figure out what's in those square roots. The top comes out to negative 60. The bottom comes out to square root of 20 and square root of 180. I still don't want to type all of that in because parentheses again. So I'm going to just figure out what the square root of 20 times the square root of 180 is, which is actually the same thing as the square root of 20 times 180. The square root of 3600 is 60. And negative 60 divided by 60 is negative 1. How satisfying is that? We have a correlation coefficient of negative 1, and it actually came out perfectly to negative 1 this time. Do you know why this one didn't come out perfectly? It was really the fault of those standard deviations. Those were rounded. I took those off the calculator and I didn't use all the decimal points. So that's why we ran into the strange rounding thing at the end, where this formula doesn't use standard deviation and everything is a nice whole number because we had nice whole numbers that we were working with. So you might even say the computation formula is more precise since we didn't have to start with those rounded values. And again, that r of negative 1 just tells me that I've got a strong, not just strong, but a perfect negative correlation. Now let's be real about correlation. Just because two things have a strong correlation even, doesn't mean that you have a cause and effect situation. A strong correlation might mean that you have a cause and effect, but you really shouldn't assume that. It could be because of lurking variables, right? Or other errors, or just coincidence. So we always say that correlation does not equal causation. Correlation and cause are not the same thing. And one of my favorite websites is tylervegan.com. Here you'll see that the age of Miss America over the years is strongly correlated with murders by steam, hot vapors, and hot objects. But does that mean that one caused the other? Probably not. If you have a sense of humor and you want to visit that website, it's pretty cool. This guy's even got a new book that he published, which would make a great gift for your favorite stats teacher. Most of the correlations have to do with death, so it gets a little dark, but it's just funny to see what kind of different correlations he finds. And it just really solidifies the fact that correlation does not always mean cause and effect.